discuss later. Thanks, Jared.
Yeah, thank you.
We will move right on to our next speaker, which is Gioia, speaking about chromospheres in cool evolved stars. So go ahead.
Yes. Okay, can you see my screen?
Yep.
Perfect. So good morning, everybody, and thank you for your invitation. And so today I will bring you all in a journey to explore the chromospheres of cool evolved stars. But first of all, let me show you the messages that I would like you all to bring home from what I'm going to tell you today. And in particular, bearing in mind the purpose of the meeting, let me touch on some of the problems that I have identified in our field and what I believe are some possible pathways toward their solutions. And so the details of the mass loss process in evolved stars are not yet fully understood. This is pretty clear. And in particular, I want to draw your attention on these kind of questions. So where does the transition from magneto-hydrodynamic driven to dust driven wind lie? And what is the mass, how is the mass loss imparted into the stellar wind from the chromosphere? And so to tackle this problem, I propose that we can, we will see how actually multi-wavelength and multi-techniques observations can really offer a solution, really exploring and probing the physics of different atmospheric layers and also the interaction within each other. And then another question identified is there a direct relationship between the chromospheric activity and the presence of dust in cool evolved stars? And is the strength of the chromosphere reduced by the presence of dust? Or in other words, what are the effects of different dust levels on the chromospheric structure and on the mass loss in giants and supergiants? And so we will see how the ultraviolet wavelength range really offers us a place where to measure the level of activity in these stars and understands the chromospheric heating and dust obscuration by calculating, for example, the emission line surface flux, and also by modeling the UV lines, from which then we can obtain stellar parameters, for example, the radial velocity of the outflow, the terminal velocity, the mass loss rates, or the chromospheric heating rates. And the last question I have identified is, what is the geometrical extension of the chromospheric region and of the molecular layers in K and M type stars? Is there a clear border where the chromosphere ends and when the wind begins, or do these regions overlap? And so I will show you how interferometry can really offer us the optimal solution to solve the resolve the atmospheric layers of cool evolved stars. And we can then use this data to calculate the geometrical extension through geometrical modeling and through image reconstruction. But what do I mean by evolved stars? Well, so cool evolved stars are represented by red giants on the left of this figure and red supergiants on the right. They contribute significantly to the chemical replenishment of the universe. And just to put it in context, one of the main open questions in astrophysics is about the cosmic origin of life. So how did we get here? And so while primordial nucleosynthesis in the early universe formed hydrogen, helium, and a small amount of lithium, we know that really most of the atomic elements necessary for life as we know it on Earth come from the nucleosynthesis in stellar interior. And so it's especially during the late stages of stellar evolution that these heavier elements then form molecules and condense into dust grains, which then starts eject into the interstellar medium via the stellar wind. So this ejection can be slower for winds of lower mass, lower to intermediate mass stars, or explosive as in supernovae for very massive objects. And so then this material directly affects the formation of new populations of stars and constitute the building blocks of planets and eventually life. And so that's why studying the mass loss of the stars is so important. In particular, for less evolved and less pulsating stars on the red giant branch, the details of the mass loss scenario is really not well understood even more. They are not really having large pulsations, or for example, they don't have large flares. So what's going on in these stars? There have been recently great advances on the study of convection and on the detection of magnetic fields, for example, in K giants. And in the outer atmospheres, the mass loss seems to be powered by magneto-hydrodynamic alpha waves. And really a lot of observational and theoretical work has been going on to study the mass loss process in these stars lately. However, really the mechanism involved in heating the chromosphere and accelerating the wind of red giant branch stars is really not yet fully understood. And so I want to draw your attention on the necessity to really study the photosphere and all the upper layers of the stars to really understand more about their mass loss. In particular, concerning K-type giants, let me tell you a bit more about them. So they have actually extended cool molecular outer atmosphere that are found to be quite common in red giant branch stars. For example, CO fundamental around 5 micron. And actually, they are quite important beyond stellar astrophysics, for example, to investigate the chemical abundance distribution in galaxies, the Milky Way halo, and they're actually laboratories to study the future of our own dying sun and of the Earth. And indeed, an increasing number of planets are being detected around K-type giants, and so improving the knowledge on the host stars is helping in understanding the planet's habitability. For example, the mass loss of our own sun was likely decisive in the early erosion of atmospheres from the inner planets of our own solar system. And so it's really of pivotal importance to derive K-giants' mass loss rates through information on their structure, interior physics, and stellar parameters. And so here I show you this figure that I produced of the schematic structure of the thermally and dynamically inhomogeneous outer atmosphere of this K-type red giant star Arcturus or Alpha Boop. And so we see the closed magnetic loops shown in pink and violet that are responsible for the hot coronal gas and are actually submerged in the chromospheric gas at lower temperature that is shown in light blue. And also I underline the location of the two molecular CO layer that are shown in red. And so, but how are the chromosphere of these evolved stars? Well, while on the sun, what happened is that it has a dwarf chromosphere and a really giant coronal loop. 6 billion years later, what happened is that the star actually, the chromosphere has evolved to be giant, and there are really dwarf corona. And so other similarities and difference between the sun chromosphere and the K and type giant chromosphere is that the one of the latter is bloated. It's not really in hydrostatic equilibrium, and this extends to the wind. And giant stars have dynamic and turbulent velocities that are higher than the one on the sun, and actually both are magnetized. And so how do we study the chromosphere of evolved stars? And so I want to show you this figure that I produced, showing how really multi-wavelength is a powerful way to study these stars, really accessing the electromagnetic spectrum through several windows, so to say, that this telescope provides us. And so in particular, I show you here a selection of telescopes that I use in my research, the one that I hope to use very soon. And in particular, today I will focus on Hubble Space Telescope and on the Center of High Angular Resolution Astronomy, CHARA. So different telescopes not only give us access to different parts of the electromagnetic spectrum, but also give us information on different parts of the stellar stratification. And so in this figure that I produced, I show you the schematic structure of this red supergiant Betelgeuse Alpha Ori, and we see underline the different angular scales that this telescope can observe at starting from 25 milliarc seconds circa. All right, so first of all, let me tell you about my work on the chromosphere of all stars using the Hubble Space Telescope. And so in particular, I have been using JHRS data of two M-type stars, Gamma Crucis and Mu Geminorum. And in these stars, what happened is that the photon scattering winds of these cool low gravity stars produce absorption features in the strong chromospheric emission lines. And so the strength and the shapes of this wind absorption are actually sensitive to the wind opacity, turbulence, and flow velocity. And so what I have been doing here is using this code called Sobolev with exot integration to model these lines and get the parameters of the flowing wind. And so here I show you normalized intensity versus velocity, and you can see the observations in green, the computed profile in black, and the computed profile based of the wind in red. And so these two stars have more or less the same effective temperature, luminosity class. Mujam has a higher mass and a lower surface gravity, and for this particular line, a weaker wind and chromosphere. And so this probably means that Mujam is likely more evolved than Gamma Group. And for a lack of time here, I'm showing you the case of only this iron 2 line that I picked. But I have extended this work to a series of self-reversed chromospheric lines of different strengths, with actually scanning a set of transition representing really a range of optical depths. And so in this way, I was really able to map the acceleration of the stellar wind. Here is another work that I have been doing with Hubble, this time with the STIS instrument. And so we have been observing a series of stars with this program called Astral that include both cooler star and warmer star. You can use your phone to scan this QR code and access this data. And so I want to show you here this portion of the UV spectra of two cool stars, Alpha Ori and Gamma Cru. So two M-type stars, and we identified the significant atomic and molecular emission and absorption features that you can see, and the characteristic of the photospheric and chromospheric continua and line spectra. And so I just wanted to show you this, as it's just incredible, the wealth of details in this spectra and just the plethora of information that we can find. And so, as I mentioned, another telescope that I have been using is Chara. And in particular, here I want to show you this preliminary work that I have been doing with also a postdoc at NASA Goddard on modeling the chromosphere of this star, Beta Ceti. And so I have been taking the data from Vega, that was one of the first generation instruments at Chara, working in the V-band, and will be actually replaced soon by its successor, Spica. So the data are shown in black. And what we have been doing here is trying to modeling with the Phoenix model atmosphere, so the atmospheric code called Phoenix, the calcium-2 triplet chromospheric line profile of the star. And so this triplet is known to be chromospheric in origin and really a strong chromospheric activity tracer in these K giants. And so the Phoenix model is shown by the solid line of different colors in the three triplet lines. And in the bottom right panel, you can see the temperature column mass profile for the model with the contribution function for each of the calcium-2 line shown in the corresponding color. And so even though this preliminary model includes only a modest set of non-LTE species, which we will extend to a complete set when we will publish all these models, and also includes only the chromospheric contribution and not yet the underlying wind, it actually closely reproduced the observation. And so my plan is now to produce a set of K-giant synthetic Phoenix spectra to really cover all the wavelength from the ultraviolet to the infrared. And so in this way, I will be able to provide a multi-wavelength view of this set of K-giants chromospheres. All right, so now let me tell you a bit more about part of my plans for the future. So I show you this figure just a couple of slides ago, and I plan to use Chara instruments to really observe the different part of these stars, and so the stratification of the atmosphere. So for example, with Mirk X, I will be able to observe in the J and H band the convective zone, and the photosphere. And so with Spica, the chromosphere, it's the chromospheric extension. Spica is the successor of Vega and will be working in the V band with a resolution up to 10,000. And with Mystic, in the K band, the molecular layers. And so I very much look forward to this project, and in particular, Spica will be mounted soon later this year on the mountain. And of course, my plans for the future also include the use of the Hubble Space Telescope. And so I have a couple of projects on these. In the first one, I want to investigate the relation between the chromosphere, wind, and dust content in a set of cool evolved stars, spanning really a wide range of gas to dust ratios using HST observations. Indeed, low resolution IUE data really show that the chromosphere persists in the presence of dust. in the outer atmosphere, but are actually weaker than for objects with lower dust content. But it's really still unknown how the dust impacts the structure of the chromosphere and the wind, and how it affects the mass loss rates. And so these observations will resolve this issue. And so here I show you the preliminary modeling with the phoenix. So we see the non-LTE versus LTE phoenix models applied to gamma crew STIS data. And so we see here only the chromospheric component, and our goal is then to add the overlying wind absorption. Another project that I have is I want to study the origin of the wind of K giants using STIS, spectroscopic observations, so resolving a set of chromospheric diagnostic lines, for example, magnesium 2, iron 2, aluminum 2. And so this observation will really help to unravel the role of the chromosphere in powering the mass loss of these stars. And here I show you previous IUE lower resolution observation that really showed the need for higher resolutions one. And so I leave you on screen the take-home messages I show you at the beginning of my talk. Thank you, and I will be happy to discuss further with you and answer your questions.
Thank you very much, Gioia. So yeah, as with before, if people have questions, go ahead and